Right. Hi, my name is Emile, and I'm presenting work on the data adaptive model predictive control of linear time varying systems with imperfect predictions. And this is joint work with graduate student Yihung Lin and Yingying Li, postdoctoral scholar James Bryce, and professors Yisong Yu and Adam Weirman. So this is a project at the intersections between control theory and machine learning. To place it in context, I'm going to first talk about reinforcement learning and how it relates to my work in predictive control, and then some specific parts of our work that use some interesting results in contractive perturbations. And then I'm going to go over some applications of this work and possible next steps. So let's start with reinforcement learning. At a high level, reinforcement learning is one of the most important paradigms in machine learning, where agents or actors learn to take a sequence of optimal choices or actions in oftentimes unknown environment. So broadly speaking, there are two classes of reinforcement learning. One, model-free reinforcement learning, where the agent or actor uses a predefined control policy to make optimal decisions in an environment. And two, model-based reinforcement learning, where the agent uses a predictive model of the environment to make optimal decisions. And you should note here that this environment here can be either an average case environment or an adversarial environment. So our work concerns model-based reinforcement learning, where the question is that we're given a system that receives predictions of its future costs, dynamics, and disturbances, and we're posing the following problem: how can we leverage these predictions to make optimal choices? So consider the example of a self-driving car traveling from point A to point B. So if the car received predictions such as in 10 seconds, a child will cross the road and face incoming traffic, or in 7 seconds, the light will turn red at the road I'm currently following, how can we design an algorithm that uses this knowledge and leverages it to provide the best route for point A to point B while maximizing constraints such as safety and effectiveness? And this is a question that model predictive control tries to answer. So let me talk a bit more about what specifically model predictive control does. So model predictive control, or MPC, refers to a class of algorithms that are used to control some processes while satisfying a set of constraints, with the slated advantage that at each time step, the algorithm receives an exact prediction matrix of the costs, dynamics, and disturbances of the system for k future time steps. And you can note here that you can define a family of model predictive algorithms parameterized by k, where k is an integer. And model predictive control works on many systems, but one example of a system of interest is the linear time varying system, or an LTV. So for the dynamics of an LTV, xt is the current state, or the state at time t, ut is the action at time t, and wt is the disturbance to the system at time t. And we really have some kind of assumption on wt, that wt is uncorrelated IID and usually Gaussian. And here at and bt are stochastic matrices which vary with time. And the dynamics of the system are given by xt plus 1 is equal to at times xt plus bt times ut plus wt. And these are the dynamics that govern the system. So note that in LTV, like most systems, you cannot choose your ideal state xt plus 1 as you wish. You instead have to choose your action ut, which then in turn influences xt plus 1 via matrices at and bt and wt. And you really have to pray that you choose the right ut that comes close to the ideal xt plus 1. But what does ideal mean here? Well, so the LTV system is actually a game. You pick your action, ut, to generate xt plus 1, but then you incur a cost, which is ft of xt ut, which has some dependency on your previous state and your actions. And then your goal is to find some actions, ut, a sequence of actions that minimizes your cost over your prediction window. And existing research has shown that any system can be optimally controlled using MPC when the predictions are completely accurate. This result is subject to further assumptions such as convexity and Lipschitz continuity. But in real life, these predictions are rarely perfect and they contain noise. But what's worse is that the prediction error tends to accumulate with time, making the prediction quality worse off in the future. And what this means is they're relying on the naive algorithm that assumes that it is receiving accurate predictions can lead to ultimately catastrophic errors. So in this work, we present an algorithm that adjusts for noise in the predictions under further assumptions of convexity and Lipschitz continuity through two tactics. So strategy one is where we adaptively tune our model on the best prediction window K. And we have a guiding quote that curiosity killed the cat, but satisfaction brought it back. And note that if we set up a small prediction window, we are really acting very short term. We aren't leveraging enough information from the predictions. But on the other hand, if the prediction window is large, then the predictive errors accumulate and the predictions become more unreliable. So it really does seem like there is some middle ground, like a sweet spot for which we can choose a prediction window that has high enough error, high enough length, such that it is utilizing some predictions, some of its predictive power, but also it's low enough such that it isn't crippled by the predictive errors that it might face. And I really like the previous quote, by the way, that summarizes the dangers of increasing a prediction window, but also the enormous rewards you can get if you're being smart about how you choose your window. And then the question is, how do we adaptively choose the prediction window K? So for this, we define a setting from online convex optimization, which is the multi-armed bandit, where every arm corresponds to the length of a prediction window. And you have K arms. The bandit is a construction from OCO, and it's an extremely well-studied algorithm. And the bandit, true to its name, will always seek to maximize its reward or alternatively minimize its loss, just like us. And the bandit starts out as completely clueless about which predictive window is best, so it assigns an equal probability measure to each arm. It then chooses an arm randomly with the probability associated of choosing each arm. And it uses the associated prediction window of the arm. So if it chooses the ith arm, it would play MPC with a prediction window of I, and it would then play a few iterations of the game while incurring the cost, which is the sum of the FTs. And then if the cost is high, the bandit is, of course, displeased. It has just made a loss. So it penalizes the arm by reducing the probability by which it can be chosen in the future. And similarly, if the cost is low, the bandit is happy, well, or less displeased. So it rewards the arm by increasing the probability by which it can be chosen in the future. And this method really allows us to adaptively select the best prediction window in response to the inputs. And specifically, the algorithms involved here are multiplicative weights, EXV3, and the UCB algorithm. Alternatively, we can try strategy 2. And I like this quote here, which really guides our approach, that trust is earned with actions. And it's the same deal here. If my trust in the predictions is giving me high losses, I need to readjust my views on how much I should trust my predictions. So more rigorously, let theta of t be some real value number between 0 and 1 inclusive. So theta of t is our measure of trust of the predictions that we get at time t. So we can choose the ut that minimizes the cost of choosing xt plus 1 in this trust determined setting. So intuitively, if theta is equal to 1, then we trust our predictions completely. And if theta t is equal to 0, we do not trust the predictions at all. So the question as before is, how do we adaptively tune our confidence of the hyperparameters? So for the discrete setting, we propose a BAPS, or a bandit adaptive policy selection algorithm, where we can just use online gradient descent to build up our confidence of the predictions. Intuitively, we can keep adjusting our trust in the predictions until we minimize the loss. For the continuous setting, we propose an alternate gradient-based policy selection, or GAPS method, which uses a chain rule to compute the partial derivatives to approximate the gradient of the cost function in this online setting. And that kind of wraps up the strategy and our overall algorithm. But then the natural question that we must ask is, how good is the algorithm? Well, so in online convex optimization and in policy selection and controller selection, we tend to measure how good an algorithm is by comparing it to the offline optimal algorithm that receives perfect information, and we calculate how much worse off our data adaptive algorithm is. And this is a pretty common standard metric for determining how effective our algorithms are compared to each other. And we find that our total cost deviates from the optimal cost by a sublinear factor of 1 over the square root of t, which is the dynamic regret standard that people in the control theoretic field usually aim for. And more specifically, our more generalized algorithm tends to outperform a special case of an earlier algorithm proposed by Eladzazan by a log t factor. But for our algorithm to work, we rely on one crucial assumption that I would like to explain and get into kind of briefly, and that is the idea of perturbation. So an earlier work by my mentor showed that if you take a state and perturb it just a little bit, and then apply the control algorithm such as MPC, or there are really actually a wide variety of algorithms in this policy selection that satisfy this behavior, where if you take your initial state and you perturb it just a little bit, and then you apply this control algorithm to the initial state and the perturbed states, then the trajectories of each of these states converge to each other pretty quickly, and particularly it's actually exponentially decreasing distance. So in generalizing our work to all kinds of controllers, we assume that they have a similar contractive perturbation property, which is a quite reasonable assumption and one that has already been shown for MPC, but can also be generalized to many other controllers. So even if you have a controller with the wrong prediction window at first, then the idea is that you can then at some point use the controller with the correct prediction window, and that will balance out the harmful effects of the bad controller. And it's quite similar to this notion of memorylessness, that a controller will forget its initial state very quickly as it tries to drive the trajectory of the state towards its optimal path. So the idea is that it is still acceptable to sample wrong controllers as long as you end up at the correct controller eventually, which our algorithm guarantees and has provable stability guarantees on. And thus we were able to really reach this balance on the exploration versus exploitation problem. And now I'd like to talk about some of the applications of this work. And I'm going to present two of potentially many applications in this presentation. So firstly, trajectory tracking. We tasked our algorithm to track the figure 8 in an environment with noisy predictions, and we saw that the model still performed really well at tracking the figure. The trajectory model does look somewhat like an 8 here. And then we also showed some very promising work for nonlinear, therefore non-convex, nonlinear but convex systems, which are considered to be much harder problems. So we simulated a quadrotor helicopter delivering 10 packages. So every time a package was dropped, the mass and rotational inertia of the helicopter would change, which makes this a nonlinear control problem. And then we let our algorithm control the quadrotor, and we track the deviation of the horizontal trajectory of the quadrotor against the optimal trajectory, which is just a circle. And we showed that the deviations were remarkably small, which is pretty promising. And we also saw that if you keep running this algorithm many times, then you eventually do just converge to a circle, which is what this figure shows here in this region. And finally, I'd like to talk about our future work. So we're reaching the conclusion of this project, and we are submitting a paper to ICML/NeurIPS. We hope to, that being said, we hope to improve this project further, and some future ways in which we can take it or this project forward include extending the applicability of our model to non-convex cost functions. Also, at the same time, removing our assumption of Lipschitz continuity. We would also like to decrease assumptions of the model by seeing if weaker contractive perturbation properties will yield the same stability guarantees of our algorithm. And then we would like to also generalize this work further using methods from online mirror descent and increase the practicality of our BAPS and GAPS algorithm by allowing it to work with a non-convex surrogate function. Yeah, and so this concludes my project. I'd also like to make some acknowledgements. So my mentors, Yi-Hung Lin, James Price, and Professor Adam Weirman, and Yang Lee and Professor Yi-Sung Yu. I'd also like to thank the Caltech SURF program and the SFP office for the opportunity to work on this project. And finally, I thank the Caltech Associates for the generous funding to this program and for letting me work on this project. Thank you.